Hello and welcome to Nkumat Online Academy. Today we want to talk about the young modulus. Young modulus is what we actually introduced in the previous lesson on elasticity. We talked about elastic constants and we said that we have three types of elastic constants. We have the young modulus, we have the bulk modulus and the shear modulus. The young modulus is the elastic constants when we are considering the area of the object, and bulk modulus is when we are considering the volume of the object. Then the shear modulus, we are considering the angle. We are going to talk about bulk modulus and the shear modulus later. But today our attention is going to be on the young modulus. Young modulus is defined as the ratio of stress to strain in an object. The ratio of stress to strain in an object. Stress actually means the force that is acting per cross-sectional area in an object. What I mean by this is that when you apply a force to a particular object, the force that is acting per cross-sectional area is what we call the stress in the objects. When, for instance, you draw your rubber band, you've applied force to the rubber band and the force is acting per particular point. You are drawing it to a particular direction. So the force that is acting per that particular direction or per cross-sectional area within the object is what we call the stress of the object. When you apply force per cross-sectional area in an object, it always results to either increase or decrease in the length of the object. Yes, it can result to increase in the length of the object if you are stretching the object. But when you are compressing it, if you want to compress an object, you are still applying force. But the force you apply now is used to compress the object. So the stress can bring about stretching or extension of length or decrease in length, depending on whether you are stretching or compressing the objects. Now, strain, on the other hand, is the change in length by the original length in the object. Just like we said that the stress produces a change in length, when we are now talking about the change in length that is produced properly, we are comparing it with the original length of the object. We call that strain. So, young modulus now, which is defined as the ratio of stress to strain, can now be said to be the force over area, then over the extension over the original length. Stress alone is force over area, and strain is equal to extension produced over the original length. So we can now write that young modulus, we represent young modulus with the symbol E. So we write that E is equal to force over area. F over A, this one represents the stress. Then this over now the strain, which is extension over the original length. Let's use E to represent our extension, and now L1 to represent our original length. So we can now write extension over L1. Now this actually means that if we have extension, that is, if the extension is not given to us straight, but the change in length is given to us, we can find the extension from the change of length by saying that extension is equal to the final length minus the original length. So if you call the final length L2 and we already have our original length as L1, we can now say that we can rewrite this equation to be like this. Stress remains force over area. Now we can now say extension is, if we are not giving the extension direct but we are giving the change in length, so we can find the extension from the change in length by saying now L2 minus L1 over L1, which represents our original length L1. So we can use this as the formula of Young modulus, or the first one that I just claimed. That is where you put E extension then over the length given to you. So it depends on what you have in the question being asked, then you know what to put in the question to get your Young modulus. Let's look at some examples. In this example 1, we are asked to find the Young modulus value of a material whose elastic stress and strains are 4 Newton per meter squared and 0.30. This 0.30 does not have any units. Please note it that stress, the unit of stress is Newton per meter squared because the unit of force is meters. If you use dimensional principle, you'll be able to get it to drive the unit of this. The unit of force is Newton and the unit of area is meter. So the unit is Newton per meter squared. Now for strain is considering length and length. Extension is measured in meter and the original length is also measured in meter. So we have now meter over meter, so they cancel themselves and then it becomes 0. So there is no unit for strain. That is why this one does not have any units. Now to find our Young modulus, now we know that Young modulus is equal to stress over strain. E is equal to stress over strain. E is equal to stress over strain. So we can now say we are giving the stress and we are giving the strain. So we just put everything into the equation and find the value. So it becomes 4 over 3.0 and this will give us 13.33 Newton per meter squared. Note that the unit of stress is the same thing as the unit of Young modulus because the strain does not have any unit at all, so it takes just the unit of the strain, which is the numerator. There's nothing dividing it. So that is why the unit of Young modulus is also Newton per meter squared. If you are conversant with pressure, you also find out that pressure also has the unit of Newton per meter squared. These three things, pressure, stress, and Young modulus, they have the same units. Now this is the answer, 13.33 Newton per meter squared. This is the answer for the Young modulus here. Now let's look at another example. In this example, we are given that a wire of length 2.00 meter and radius 1.0 millimeter is stretched by 25.0 millimeter on application of a force of 10 to power 3 Newton. Calculate the Young modulus of the wire. Okay, first of all, because we are considering area in this Young modulus, it is very, very important that you monitor the object being considered because the area of different objects are different depending on the shape. Wire, the way we calculate the area of wire is different from the way we calculate the area of a rectangular block because they are two different shapes. The shape of an object determines its area. Now, for this one, this is a wire. For a wire, the cross-sectional area of a wire is given by pi r squared. Pi r squared. That is what we use to get the cross-sectional area of a wire. Now, but before we get that, let's do our conversion. We can see that some of these values here are given in millimeter, while others are given in meter. The equation we are considering, or the Young modulus we are considering, the unit is in Newton per meter squared. So we are going to convert the millimeter to meters. So that is the first thing we are going to do, unit conversion. In this unit conversion now, we know that 1000 millimeter is equal to 1 meter. So we say 1000 millimeter is equal to 1 meter. Therefore, 1 millimeter is going to give us what? If you solve this, it's going to be, let's do cross multiplication. That is this one coming to this one, and this x going to this, and then that is going to give us that x is equal to 1 over 1000. X is equal to 1 over 1000. That gives us 0.001 meter. So we have converted 1 to 1000. Now let's convert the 25.0 millimeter again to meter. We've converted 1 to meter, 1 millimeter to meter. It gives us 0.01 meter. 0.001 meter. Now let's convert 25 millimeter to meter the same way we converted the other one. So similarly, we see that if 1000 millimeter gives us 1 meter, 25 millimeter will give us what? So if we do this conversion, we are going to get 0.0025 meters. So this is the meter. This is the meter equivalent of 25 millimeter. So now we have converted the units. We now start solving. We have to get the area because we know that area of a wire, the cross-sectional area of wire is equal to pi r squared. So we have yeah 3.142, which represents the pi, that is a constant, times by 0.001, then raised to power 2. So this will give us the cross-sectional area of the wire. Now we put this as the value of the area of the wire, and we put the force to get the stress. And now we substitute again the other one, converted the 25 to get the strain. So our force now actually is our strain, our stress, which is force over area, is now Our force is 10 raised to power 3. Our force is our force is 10 raised to power 3. So we put it there and put the area. Okay, so this is what we have as the area, and the other one as the force. So with this, we are getting the stress of the material. Now let's look for the strain. The strain is the extension of the original length, and the extension given to us is, we've converted it from 25 to meter, which gives us a 0.0025. How do we know that this one is the extension? In the question, we are told that it is stretched by this. That it is stretched by this. This by always shows that it is an extension, the increments. If they say it is stretched to, then we know that that leads to a new length, but by means that this is the increment itself. So this is the extension. So that is why we are using it as the extension. So we put this value over the original length. Original length is 2. So the original length is 2 meter. There is no conversion to do there because it's already in meters. So we now say that our Young modulus is equal to stress over strain, which is what the values we now have for the stress over the values we now have for the strain. We put everything together to get our Young modulus. E is equal to stress over strain now, which is equal to, this is equal to, stress is 10 raised to power 3 over 3.142 times by 0.001 raised to power 2. Now this is the first fraction divided by strain. Strain is another fraction, so we put divided by, this is representing this division sign. So let's just write it with this division sign. Now strain is 0.0025 over 2. Now when we have two fractions being divided, we can change the main division sign, which is this one, to multiplication, and then invert the second fraction. To invert it means that the one that is under, we bring it up, and the one that is up, we bring it down. This first one will remain the same, but this one, we invert it when we change this one to multiplication, and that means that we have 2 over now 0.0025. What we are now going to have is Young modulus is equal to so it's going to give us now 10 raised to power 3 over 3.142 times by 0.001 raised to power 2 times, we have now changed the division sign to multiplication sign. Then we have inverted the second fraction, 2 over 0.0025. If we solve this, we are going to get that our E is equal to, E will give us 2000, 10 raised to power 3 is 1000, times by 2 is 2000, and then we divide it with the denominator. We are now going to have 2.3 times by 10 raised to power 10 Newton per meter squared. So this is what we are going to get as the answer. Approximately, this is what we are going to get as the answer. So this is how to calculate this. So I've actually solved a very simple question on this Young modulus and a very complex question on Young modulus, so that no matter how the question comes, you should be able to answer it very well. So this is it about Young modulus, and I believe that this lesson is very clear. Thank you.